Hello. Welcome to the delayed Wednesday meeting of the Semantics group, or meeting of our course Semantics group. Instead of BBB, I'm just doing it with slides that I'm pre-recording because of the Dies Academicus. Okay. So what I want to talk about today, so these slides are far too long for one meeting. So I imagine that what I'm going to do is I'm going to talk about them today for a little bit, and then next week we're going to continue talking about them. Okay. Moreover, these slides have a lot of examples in them, uh, and these are examples about how to use the syntactic framework in sort of a non-standard way, maybe, to analyze familiar phenomena. And as that's not the focus of this course, I'm going to skip over a lot of these examples. I'm going to go through them extremely quickly, too quickly for someone to really get much out of them. If you have taken the syntactic decomposition course last semester, then you'll find them very familiar. You'll recognize many of them. Okay. Again, as the point of this course in general is to do compositional semantics, peculiarities of the English auxiliary system, or analyzing English A movement is not particularly relevant. Okay, so I'll talk about them as far as it's useful, maybe for intuitions about how to use the system, but I'm not going to deal with them much. Right? The main point of today's lecture is to give you a better understanding of the formal framework that we're going to be using to couch our semantic analyses in. Okay? And last time we talked about derivations, which I think of as the fundamental structures of syntax. And the blog post from last time focused a lot on what we're going to be talking about today. And so I'm hoping that I'm going to use a little bit different notation, whereas in the blog post I used multiple dominant structures. Here I'm primarily using trees, but again, I think it doesn't matter. I think that derived structures are largely unimportant anyways, but this sort of proselytization is not my main goal right now. I want to teach you about the way that the syntax is working, not about the way that syntax works necessarily, but about the way that the syntax of our particular grammar works, so that when we attach meaning to it or try to interpret it compositionally, we'll have a better understanding of what exactly it is that we're trying to do. Okay, so what are derived structures? Well, those are the things that we usually think of when we talk about syntax. Okay, they're the things that we're building up during the course of a derivation. Okay, now usually when you read papers and you see structures, they're binary branching trees. Okay, and they're binary branching trees that are ordered in two ways. Okay, so a tree is a particular kind of graph. It's a directed acyclic graph, directed because it matters whether there's an edge from one node to another or back, right? Because there's a difference between parents and their children. It's acyclic because you aren't allowed to have any loops. It's also a rooted directed acyclic graph. And it's moreover it's rooted because there's one particular node that is the descendant of all the other nodes, namely the root. And it obeys the single mother condition, which says that if any node has a mother, it has just one mother. Okay, so this is what distinguishes a, say, tree from a multiple dominant structure, just sort of graph theoretically. That doesn't really matter. But moreover, above and beyond just being a tree, the structures that we derive in minimalism in general are ordered trees, and they're ordered trees in two ways. First, they're ordered in terms of linear precedence, which corresponds to spell-out order. So which sister is pronounced before the other. Okay. And they're ordered as well in terms of projection. Which sister projects over which other sister? Okay. So linear precedence is known to everybody, right? When you write down a tree, you write it in a particular order, and you always write it, a syntactic tree, and you always write it in the sort of reading order, right? So you write it with the thing that you pronounce first, farthest to the left, and the thing that you pronounce last, farthest to the right. This is true even if you adopt the idea that syntactic structures are actually linearly unordered, right? As many people do nowadays. Our trees, our derived structures, are going to be linearly ordered, or are going to be ordered according to linear precedence, according to pronunciation order, not because I'm taking a strong position against Cain or against anti-symmetry or whatever, or that I firmly believe that they need to be ordered, just because it's easier. You have to pick some order when you write it down. Everyone already writes trees down with this order attached to them, even if they pay lip service to the idea that in actuality they're unordered, right? So even if people say that they want their syntactic structures to be unordered, they always behave as though they were ordered, right? This is not a critique. It's just when you write them down on a page, you have to order them somehow, okay? The other order relation that trees have in syntax is familiar to everybody, but most people don't recognize it, don't recognize what they're doing. So one of the tenets of, let's just say, generative grammar, although many other frameworks also adhere to this, is that in a structure, or is that structures are endocentric. Structures are headed, okay? What does that mean? That means that if you have two sisters, one of them has the head of the entire phrase and one of them doesn't, okay? The one that has the head of the entire phrase projects over the one that doesn't. The one that doesn't is either a complement or a specifier or an adjunct of the one that does. Okay. This is a relation between sisters which orders the tree. So if we believed that, if we really believed that syntactic structures were unordered or were not ordered according to the pronunciation relation, and we had to write them down on the page, we could write them down according to the projection order, according to which that sister would come first that actually had the head of the structure. Okay? But we don't. And I think because people just don't understand that this is really a ordering relation in the same way that linear precedence is. None of this really matters. It's on the slide and I'm reading it to you. It sort of matters in that it's good to understand what you're doing. Okay. So the traditional way to represent this information is on the slide. It's been on the slide these entire 20 minutes that I've been talking, and it's using the X bar notation. Okay. So X bar notation encodes this projection relationship between sisters using node labels. Okay. It's a way to encode an ordering between your nodes, not using the sort of left to right ordering that God gave us via writing things on the page via physics, but encoding it via man-made labels. Okay, there's no right or wrong. It's just the way it's done. The way linear order is encoded, or linear precedence is encoded in these trees, is familiar, right? Left to right, easy. The way projection is encoded in these trees is also familiar. It's just not It doesn't feel familiar because you don't know that you're doing what you're doing. Okay, so what you're doing when you write these node labels, x, x bar, xp, is you're encoding via these node labels an ordering relation between sisters. So let's look at the xp node. The ordering of relation between its two daughters, who are sisters, the daughter, the specifier daughter, that triangle, and the x bar daughter, is given by it specifies that the x bar daughter is the one that projects over the other daughter. How does it represent that? Well, because the x bar daughter has the same name as the xp daughter. It's an x, and because it's a bar, it tells you, oh yeah, I'm one below the xp. Okay, so by that information, you're encoding information about which daughter projects over the other one. Let's look at the x bar subtree. It has two daughters, an x and a triangle, the complement. Which one of these projects over the other? Well, of course, the x projects over the complement because it has the same name as the node above it, as its mother, right? Modulo the bar. Okay, so this x bar naming convention encodes information about the projection ordering relationship. Okay. But, who cares, right? Or rather, that's what matters. Who cares? What matters is that this information is encoded in the tree. That's a linguistic claim. What isn't a linguistic claim is these node labels have a deep metaphysical meaning, right? If you thought they did, then you were disappointed when Chomsky said, no, they didn't in the Minimalist program. Okay, so in the Minimalist program, Chomsky said, hey, we don't need this weird naming convention, x, x bar, xp. We can just write x over and over again, right? It's the same information. It's the same information. Now, instead of saying, okay, which sister projects over the other one, well, let's look at the mother and see whether the mother's name is related in the appropriate way to which sister's name. No, we don't do that. We simply say, that sister projects over the other, which has the same name as the mother. Okay? This is in the middle. This is the tree in the middle, the one that just has x's. Okay? So here, instead of writing x, x bar, xp, you just write xxx. So easy. Okay, there's another variation on this. This is bare phrase structure. Another variation on bare phrase structure where instead of writing node labels as categories, you write them as lexical items. So if X were a projection of the lexical item, I don't know, monkey, so X were an N, instead of writing monkey dominated by N, N, and N, you would just repeat the lexical item monkey. Okay? But it's the same idea. Which sister projects over the other one? Well, it's the one that has the same name as the mother. Okay? Now, this is an encoding scheme that that runs into trouble sometimes, right? So this is a nice way of representing this information, as long as you, in most cases, but it breaks down in some cases, namely if you have, say, a copy of the same lexical item merging with itself, right? Maybe if you're making a noun compound and you have house monkey, you have tree monkey, and you have monkey, right? Maybe you got a whale monkey, you got a cow monkey, and you got a monkey. Okay, whale monkey and cow monkey, if you are having a lexical item labeling scheme where nodes are labeled with lexical items, it's clear who projects over whom. But if you have a lexical item labeling scheme and you're analyzing monkey, well, the parent is going to be monkey, but you don't know, but both daughters have that same label, and so which one is projecting over the other one? Well, your representation, your notation, doesn't actually succeed in conveying the information that you want in this circumstance. Okay, so it's a cute representational scheme. It just breaks down in some cases. Okay, that's one way of looking at it. Another way of looking at it is this representation scheme reveals a deep truth about our cognitive apparatus, and the fact that this representation scheme doesn't work in some corner cases is a deeply revealing and important fact. Okay, by the slight disdain in my voice, I figure you can figure out where I stand on this issue. But some people think that, and I've been wrong before, and maybe they're right. Okay, I don't know what it would mean if they were right. But yeah, all this stuff about symmetry breaking, that's what it's about, right? People have taken this representation, this notation for encoding information about projection and suddenly viewed it as the gospel truth, and it's, Moses came down with the tablets of God, and on it was written, the labeling that the brain uses is lexical items, okay, and therefore symmetry breaking. Okay, from my perspective, the important thing is not the notation that you use. The important thing is the information that the notation is being used to convey. What is the information that the notation is being used to convey? Why, it's information about which daughter projects over which other one. So we should probably use a notation that succeeds in conveying this information. What's a good notation? Well, I like the notation on the right. The notation on the right uses not copies of anything or X bars or whatever. It uses arrowheads, the things that are also identical to greater than and less than signs. It uses arrowheads to point to the daughter that projects over the other one. Okay, so all three of these representations are representing the same thing, like literally the same thing, the same tree with the same projection information. They're just encoding that information differently. Okay, so here on the tree on the right, if we look at the root, we ask, well, which daughter projects over the other? And we look at the root, and the root is pointing to the right daughter. The arrowhead is pointing to the right. I think that so this is my right, but it's pointing left. I mean, it's pointing in this direction. It's pointing towards this daughter. Oh God, this is confusing. It's pointing toward this daughter. It's pointing toward the daughter on the right, not the specifier. And therefore, well, that must be the daughter that projects. What about the what used to be the X bar, right? The middle node. Well, which of its daughters project over the other? Well, it's pointing towards the X, right? So that's the one that projects, right? Super easy. Okay. With the elimination of the X bar scheme, right, came also a difference, which is that instead of having unary branching, sequences of unary branching nodes, like back in the olden days, the pronoun he would have the syntactic structure dp, d bar, d he, with no complements or specifiers, because everything conformed to X bar theory. Now, you just say, well, if there are no specifiers or complements, there's no extra structure, right? It doesn't really matter, but that's a difference from back in the day. Okay. The representation that I'm going to use to encode the projection information is this one on the right, the one with the pointy arrows, because it's simple. Okay. I don't care about representation. I only care about information. Okay. I care about information, not about the way I'm representing it. Okay. I care about representation sometimes, but not now. Now I only care about the information. Okay, so specifiers and complements. Complements used to be the non-projecting daughter of X bar, and specifiers used to be the non-projecting daughter of XP. Now there are no bars or P's, but complements can be redefined equivalently as the non-projecting sister of the lexical item, or a sister of a lexical item, and as a non-projecting sister of a non-lexical item. So first merged things are complements and later merged things are specifiers, okay? These are just the basic notions of phrase structure. You guys learned this in your first syntax course, okay? Just going through this quickly, or maybe not so quickly. Heads, what are heads? Well, you all know what heads are. Heads are the leaves which project, okay? But if we have an expression, the head of that expression is where you land when you follow the arrows down the tree, okay? We can define this in a very formal way, giving sort of an algorithm to figure out where it is, which is what I just told you. The head of an expression is itself if it's a leaf, right? If it doesn't have any daughters, if something doesn't have any daughters, it's the head of itself. If you have a tree whose root is pointing to the, I'm sorry, that's right, the left, that's harder than you would think. A tree whose root is pointing to the left, then its head is the head of its left daughter. And if you have a tree whose root is pointing to the right, then its head is the head of its right daughter. So in this tree here on the screen, we have the root of this tree is pointing to the left, so its head is the head of its left daughter. And the left daughter, its root is pointing to the right, so its head is the head of its right daughter. And the right daughter is a leaf, and so its head is itself. Okay, so the head of that tree there was L2, right? You just followed the arrows down until you landed a leaf, and that's the head. Okay, so how does this work? Well, we take a derivational algebraic perspective. This is just minimalism in general, right? There's no difference to what we're doing than minimalism, right? It's just we have this one notational difference, but other than that, everything is exactly the same. Right? I'm just rephrasing the stuff you know in a way that I find more congenial. Okay. In the algebraic perspective or derivational perspective, you have basic elements, which are lexical items, and ways of building complex things from simpler things, and those are the grammatical operations. The language of the grammar is the set of things that you can build from the basic elements using the available operations, right? Everything you can build is part of the language of the grammar. What are the basic operations? Well, one of them is merge. You take two things and you stick them together. Okay? So, that's an operation. How does it work? Well, the way I described it here, you can put any two things together. You can put the together with the. You can put monkey together with monkey. You can put whatever together with anything else, right? It doesn't matter. No, it's just to put two things together. Okay? This is how Chomsky sometimes talks about it, how Borer sometimes talks about it, right? Free merge. Just put two things together. Syntax doesn't care. But of course, syntax does care, right? So we all know that things can't just be randomly stuck together, right? So in English, you can stick a verb and a noun together, John laughed, but only in a particular way, right? John laughed, but not laughed John, right? So merge should be defined on John and laughed, but not on laughed and John. Duh, right? We all know this. So what is the answer here? Well, the answer is the same as in every other grammatical framework, everywhere. Everyone has this problem. This problem, I put it in air quotes because, it's obvious what the answer to this problem is. It's so obvious that most people don't even bother thinking of it as a problem, right? But if you have sort of free merge, then suddenly the problem becomes salient. The problem that everyone has, that everyone solves in the same way, becomes salient. And so you have to actually say what you do. Okay? Everyone's solution is the operations, the grammatical operations, are sensitive to properties of the expressions. Okay? So John is a DP. Merge wants a DP to make a VP, and that's why they can be put together. Okay? So this ran off the slide, but it doesn't matter because I'm talking to you. Okay? So what does it mean that expressions have properties? Well, they have features. Right? Feature is just another word for property, but we reify features. Okay? Features are reified as things. Okay? Do they have to be things? No, they could be sort of emergent properties, right? But however these properties come to be, expressions have to have them. Okay, and they're relevant for the derivation. They're relevant for syntax. And so whatever they are, right? I don't care what they are. We're going to give them names so we can talk about them. Okay. So I'm going to say, this slide is busy, right? It has a couple of different things. There's a notation box. Okay. And this is, well, maybe let's look at the thing to the right of the notation box, which is supposed to be an example of what that is. So John is a DP, right? That's what I said. That's going to be reified here as John having the feature D. Okay? And more generally in the notation box, something is an X, like an XP, a VP, a DP, a PP, whatever P, what category, just in case it has feature X, or rather, if we say that something is a PP or a P, then we're going to write that down as that thing has the feature P. Okay. Now back to the right of the box, laughed combines with a DP on its left to give a sentence, an S. Right? So laughed has features D equals, that's one feature, and S. D equals means I want something on my left. And moreover, the thing I want on my left has to have the feature D. Okay. So back in the notation box, if something combines with an X on the left, we say it has the feature X equals. If something combines with an X on the right, we say it has the features equals X. Okay. So the choices, this is different, by the way, for those of you who were in the syntactic decomposition course. In that course, we used a little circle, filled in circle symbol. Doesn't matter, right? It's notation. What matters is not the notation. What matters is the information that the notation conveys. Okay. Here, the information that this notation is supposed to convey is what kind of thing you want to combine with, and what direction you want it to be on. Okay. So, yeah, there we go. Equals. The reason why it's an equals, there's actually a reason. It's not a good reason. It's a sort of an intuitive reason. It reminded Ed Stabler, I think, of chemical bonds, right? So you imagine that you want to combine with something on your left. Well, that means that you are on the right-hand side of that chemical bond, and the thing you want to be bonded with is that X. Okay? So there we go. And if you want it on your right, you're on the left of that chemical bond, which is why there's nothing there. That's you. And there's a chemical bond, a double bond, and the thing you want to combine with is on your right, and it's an X. Okay? If that's useful, great. If it's not useful, it's easy to remember anyways. Okay? What is important also is that categories are structured. Okay? So laughed isn't a sentence until it's combined with a DP. Okay? What does that mean? Well, that means that even though laughed has the feature S, something that wants to combine with an S wants to combine with a real S. Laughed isn't able to combine with something like that because it's not really an S yet. It's only an S after it, combines with a DP. Okay? So that means that features, the categories that something has, the features that it has, need to be ordered with respect to one another. So we want to say that laughed has first feature D equals. It wants to first combine with the DP on its left, and then it will be an S. Okay? All right. So this is very similar to the categorical grammar stuff that we saw. In fact, it's extremely similar. One major difference is that in categorical grammar, you can have higher order categories, which means you can want to combine not just with atomic things like a DP or an S or a VP or whatever, but with things that are unsaturated. So in categorical grammar, you can want to combine with something that wants to combine with an NP on its left to become an S, right? Here, we can't do that. We only have first order categories, first order features. Okay. If you didn't understand that, it doesn't matter. So lexical items, that was sort of the intuitive introduction. Lexical items are sort of combinations of sounds and structure, also meanings, but we're not talking about that yet. Okay. The structure that lexical items have are feature bundles. And feature bundles are lists of features. Okay. And I'm going to separate them with periods, just to make it easier to see, right? If I just wrote them all together, we would have D equals S, and it wouldn't maybe be clear who the equals belonged to. Okay, but here it's clear. We have a D equals, and then an S. Okay, again, notation, who cares? Information is the important thing. Okay, so a lexical item, again, for laughed would have to contain information that it is a particular lexical item, namely laughed, and that it has a feature bundle of a particular kind. Okay, so this actually glosses over an important distinction, which is that a lexical item, I think, doesn't need to have any morphophonological information on it. It just needs to indicate which lexical item it is, right, which lexeme it is, and its feature bundle. The morphophonological information is recorded in the interface map. It's a property of the interface. Similarly with the semantic information. The semantic information is a property of the interface, but that doesn't matter. Usually you write things down where a lexical item, you'll write down actually its morphological or phonological form together with the features. Doesn't matter. Okay? And I'm going to write this pairing of information down by separating the morphophonological part from the feature bundle part by a colon. Okay, so here in this tree, the specifier, or actually it's not a specifier, the leftmost leaf is a lexical item, or it's a pair of a string and a feature bundle. The string is ABC, and it's separated from the feature bundle by a colon. Right? No reason other than to separate these two things visually without having to put, angled brackets and a comma, right? Doesn't really matter. Okay? So lexical items are pairs of strings and feature bundles, and leaves in our trees are pairs of strings and feature bundles. Right? So we see one of these leaves, the rightmost leaf, has no string, the empty string, and no feature bundle, the empty feature bundle. Okay, that's what this epsilon indicates. So the epsilon to the left of the colon is an empty string. The epsilon to the right of the colon is an empty feature bundle. Okay, so now that we have introduced features, categories, as ways of controlling merge, now we can reformulate merge so that it's only allowed to apply when the categories are right. Okay? So merge on the right works if the pink guy, the one that's going to project, if its head, which is indicated by following this line from the root down to a leaf, which is what we do when we try to figure out who the head of an expression is. You follow the arrows down until you land at a leaf, and that's the head. Here we followed the arrows down. That's indicated visually by this squiggle until we've arrived at a leaf. That leaf has features equals X and then some other stuff. So what it wants is an X on its right. And we want to combine it indeed with something whose head is an X. Its head has features X and then something else. Right? So the first feature of the projector is equals X, and the first feature of the head of the projectee is X. They match, so we can put them together. How do we do it? We put them together in the way that they're supposed to go, right? The pink guy wanted the blue guy on his right, and by golly, the blue guy gets put on his right. Moreover, instead of just a dot, we have an arrow pointing to the left because the left-hand guy is the one that projects. Okay? It contains the head of the entire thing. So the purple guy or the blue guy is either a complement or a right specifier of the red guy. On the left is exactly the same. If you merge a red guy and a blue guy, where the red guy wants something and the blue guy is something, to want something is to have a feature that says of the form either x equals or equals x, and to be something is to have a feature of the form x. So red guy wants an x, blue guy is an x. You can put them together. This time the blue guy goes on the left because the red guy wanted his x on the left. Simple. Okay. Okay. So wanting something, desires in this world, contra Buddhism, get fulfilled. Okay. Once your desire to have an X on your right or left has been fulfilled, has been satisfied, you no longer have that desire. That desire is gone. Right? So it's possible in this system to achieve nirvana, having no more desires. Yay. Okay. So how does this work? Well, the leaves of your trees contain sequences of features which determine when an operation can apply. Okay. Once an operation applies, the features that licensed that application no longer need to be there. They're checked. The desire has been fulfilled. Okay. So once you have your desire satisfied, your desire is gone. Once you satisfy someone's desire, you can't then satisfy someone else's desire, right? Once you get married, you can't go and get married to someone else. So this is what's happening here. We have symmetric feature chain. Okay. From one perspective, we can think of operations as trying to remove features from trees. That's their telos. They're aiming at removing features from trees. Okay. I think maybe Norbert Hornstein, maybe Howard Lasnik, I don't know, talked about features as viruses, and so you wanted to get rid of them. Right. This is why they said that, because this is a sort of natural thing to think about a symmetric checking system where features license operations. An operation removes features. Okay. So in the language of a grammar is everything you can build from the operations in the lexicon, using the operations from the lexicon. Okay. A lot of that is, maybe like praise Mary. Right? A VP praise Mary. That's not a sentence. You can't go around saying that. So we're interested in everything you can build, because the things you can build can be used to build other things, right? So everything you build is interesting. But not everything you build is of an equal ontological status, right? Some of the things you build, like sentences, people actually say. Right? Those are the things that people say. Whereas other things that you build, like VPs, can be part of what people say, but they usually aren't things that they say on their own. Okay? So we want to talk about things that people say and somehow identify them so that we can speak of those things. Of all the things we can build, these are special. Okay? So there's this notion of being well formed, or an expression being complete, meaning it's done, right? It's achieved nirvana. So when have you achieved nirvana? When you have no more desires, right? So all of the features should be gone, except maybe one feature which says an I am an S, or an I am a particular category. right? So the head of the tree, the head of a well-formed or complete expression has one category and one category only, has one feature and one feature only, and that is a category feature, like I'm an S, I'm a D, I'm a V. It has no desires and no lexical items, no leaves elsewhere in the tree have any more features. So all of the features everywhere in it have been eliminated, but for its single solitary category feature. Okay, then it is complete. Okay, it has been made one with everything. And then the complete sentences are complete expressions whose head has category S, or whatever category name we give to sentences. Okay, so we can define this in a linear way, but it doesn't really matter in a super sneaky way. Right? This is how we could define merge and move without drawing pictures. Right? It doesn't matter. A T is a tree, and T prime is a tree too. A tree with a superscript feature means a tree. Take a tree and add that feature at the front of that tree's head's feature bundle. Okay, and the reason that that's a useful notation is you can talk about feature checking. So in merge, T1 superscript equals X, comma T2 superscript X. That means you're merging T1 and T2. The first feature of the head of T1 is equals X, and the first feature of the head of T2 is X. Oh, that's the case in which we're allowed to merge T2 on the right. Great, so what do we get? Well, we get a tree whose mother points to T1 on the left, and on the right is T2, but in both of these, their first features, namely equals X and X, have been deleted. Okay, that's what this notation is supposed to represent. It's a nice, convenient way of writing things down. It doesn't matter. Right? It's the same as the picture we just saw, without fancy colors. Okay, it's more precise. So now, that's a description of the structures that we build. Okay, now we have a descent into a case study of English auxiliaries that culminates in a modern version of Chomsky's affix hopping analysis. Okay, you might be wondering, well, where's all the movement, Greg? And the answer to that is it's after the English auxiliary section. So first we're going to introduce something like head movement, but the reason we're going to introduce head movement is as a way of concisely representing the generalizations that we see in these sentences. Okay, so in good linguistic tradition, I have morbid sentences. And in good computational tradition, we have morbid sentences that we can analyze perfectly, right? Without drawing triangles and saying, oh, I don't know how this is supposed to be analyzed, right? So simple morbid sentences. Okay, so here are four. John died, John will die, John had died, John has been dying. Okay, how do we analyze these? Well, let's assume they're divided up into a subject and predicate, and the predicate's right branching with elements to the left projecting over those to their right. Why do we assume this? Well, we can try to justify it, but let's assume it right now. Okay, let's start from here. This is sort of a halfway traditional analysis. Okay, so John died has the structure there. John will die has the structure there. Super simple. Right. So in particular, the subject does not project over the predicate, rather the predicate projects over the subject. Okay, that's why in John died is the head, and in John will die, will is the head. Why is will the head and not die the head and John will die? Because I said so. Okay, this is a historically controversial position. Nowadays, it's sort of canonically accepted in the transformational literature, but at one point in time, this was a controversial thing. Okay, it doesn't really matter. I just want to assume this because you guys all halfway believe this anyways, and it'll be easier for us to get off the ground. Okay, here's a bigger example. John has been dying. John has been dying. John has been dying. Different intonations have different meanings. Doesn't really matter. Again, the predicate has been dying. John is projected over by the predicate. The head of this structure is has, as we can see there. The complement of has, been dying, its head is been. Okay? That's just how we're going to analyze it. This isn't justified. I'm just telling you this is how it's going to be, right? Okay. So what do we do when we have data? We want to analyze it. How do we analyze it? We write a grammar that generates it. How do we specify a grammar? Well, we need 4 things. We need the features we're going to use, the lexicon, which tells us which feature sequences are assigned to which words, the grammatical operations, well, this is just going to be merge at the moment, and we need the start category. The start category specifies what kind of complete expressions we're interested in, right? In writing a grammar, the language of the grammar is going to have a whole bunch of things. It's going to have everything that we use, every incremental step that we use in building something up. That's an expression that the grammar generates, right? So we need to say, of the expressions that our grammar will generate, which ones are we trying to model as sentences? Okay, and those are going to be the complete expressions of a particular category. And I'm going to call this category S for start or sentences. Often it's CP, right? Or maybe TP, depending on, your choices. But here I'm going to call it S because it reminds me of sentence or start. And it's, for those of you who are reading syntactic structures in Paula Fenger's class, or Paula Fingers, I don't know how to say her name. Is she? Yeah, whatever. In her class on head movement, Chomsky uses S2 because that's what she did back in the day, right? Okay, so those are the 4 things you need to have to specify a grammar. I've already decided what the last 2 are going to be. So all that's left is to determine the features we're going to use and the lexical items that we have. Okay, that's what we need when we give a grammar, when we analyze something. Okay, so let's think. Here's one of the things we want to analyze. John died. We know we want to analyze it as a complete sentence. Okay, so we know what its head is. It's died. We know how to put things together with merge, and we know that merge checks features. So in order for John died to be a complete sentence, or in order for us to analyze John died as a complete sentence, that thing there has to have just one feature in it, namely S. On died, and John has no features. Okay? So, what features do John and died have to have in order to combine into the structure above so that died has just the feature S? Well, easy. You can only build that structure there if John and died are lexical items with the following feature bundles. Okay? And by X, I don't mean the particular feature X, I mean any feature X. Any feature with any name X. The crucial thing is that the feature that John has to be a category feature, and the feature that died has to be a selection feature. It has to be of the form X equals. And they have to be the same feature name. Right? Because died has to want the kind of thing that John is in order for John and died to be allowed to combine via merge. Why does died have to have the selection feature? Why can't John have it? Well, because in the tree that we have there, died projects over John. Right? And the thing projects that has the selection feature. Okay? So those lexical items have to be the ones that we used. Okay? But again, it doesn't really matter what name we choose for the feature that John and died share, right? I called it X there, I could call it Y, I could call it monkey, I could call it Bill. Doesn't matter, right? All that matters is that they match, okay? Not what they're called. The information that's encoded in these features, the relevant information that's encoded by feature names is which features can match with which others. The information that any other information is irrelevant. So the fact that X is whatever letter of the alphabet it is, completely unimportant. Okay? And so let's just write D instead, because that's sort of, traditional. It's not as traditional as it could be. We could write N, but there's been a disagreement about that, and nowadays the D camp sort of in the majority. So let's write D. Okay, let's say that John, the feature X that John has is actually a D, and the features that Died has then are D equals and S. Okay, we can pick the name of the feature; it doesn't matter, but that shape of feature bundle is the one that the relevant lexical items have to have. Okay. We can do the same reasoning, right? So John will die. Will in that thing, that's a complete sentence, and so we have to analyze it as a complete expression of category S. That means will in that John will die structure has the only feature in the tree, and it is S. How does will die get put together with John? Well, John has some feature X, so we decided previously that it would be D, but let's just keep on with X. John has some feature X. Will wants to combine with something like that on its left, so Will has an X equals feature. Great. And so we put that will die thing together with John. Okay. And that right-hand structure, well, will is the head, so it had to have the equals feature. Die is its argument, it's on the right, so it has to be an equals y feature for some y, and die has to have the y. Okay, so will has to have the features equals y, x equals s, and die has to have the single feature y. Okay, that's just what has to be in order to get the structure that we want with the feature that we want, s. Okay. We're not being creative, we're not being linguistic, we're not analyzing some phenomenon, we're just reasoning, right? We're doing grammatical reasoning. Your grammatical framework, the rules of your grammatical framework allow you to reason backwards from what you want to how you could have gotten it. And in this case, because the structures that we're writing down are very rich, they have a lot of information in them, they in fact have enough information in them that it's unambiguous as to the features that things have had to have had in order to construct them. I say unambiguous even though that's not quite the case. We've seen already that the names of the features aren't completely determined by the structures that we see here, right? So we've lost some information about how we put it together, namely the names of the features, but we've kept enough to sort of recover them up to renaming of features, because who really cares about feature names? Okay. And again, because no one cares about feature names, or no one should care about feature names beyond encoding which features can combine with which others, or which features match which others, let's just call the y feature here that die has V, and the x feature that here that John has D. And so then our lexicon looks like that. John will die, where John has a D feature, will has an equals V, D equals S feature bundle, and Die's feature bundle is also just V. Okay. All right. Does this work? Yes, it works. You guys can figure it out yourselves. Okay, so in exactly the same way, from this structure that we've written down here for John has been dying, we can get the following lexical items: John, been, has, and dying with those features. Okay, no ambiguity, just totally straightforward. Okay. So we had a couple of sentences to begin with. So John, I figured what they were, but I've added a couple more. Basically the entire English auxiliary paradigm without negation, or do support, or subject auxiliary inversion. And these are the lexical items that we end up with. Okay, totally straightforward. Once we decided on the derived structures that we want, which was admittedly a little ad hoc, the lexical items that we need to have in order to get them, totally determined. Okay. Now, this is a bad analysis, right? Why is it a bad analysis? Well, because if you look at it, you see there's a lot of regularities in there. that we're not accounting for, right? It's not as bad as just a list of sentences, right? A list is the ultimate in redundancy and unexpressed regularities, right? There's no regularities you bothered to try to find. But, there are regularities in this lexicon that we just didn't encode, right? So look, let's just look at some of them. So I've organized them sneakily into groups. The group on the left is all the lexical items that somehow contain the root die. The group far on the right is all the lexical items that somehow contain the root B. The one on the bottom middle is all the ones that have the lexical item have. They don't really have these in our analysis, right? They're totally different lexical items, but intuitively, is, was, be, and been are all forms of the verb be, right? Okay, but that's not encoded here. But let's look at these. So all of the be forms, their feature bundles are similar, right? They all start with equals prog. Look at that. All of the have forms, their feature bundles are similar too. They all select for an equals perf. All and only the tensed forms. So those guys in well, I didn't actually order them in a useful way. All and only the tense forms, died, dies, has, had, is, was, only these guys and all of these guys select an argument, a D, and also will. Only they select a D. And moreover, they select a D and end an S. Okay? Yeah. So that's a robust group of regularities here. Okay? And what does that mean? Well, it's not so bad. The lexicon isn't that big. But these missed regularities evince themselves or manifest themselves when we try to expand our analysis. When we try to extend our analysis so that we can deal with more verbs, like open class lexical items, like laugh, right? Laugh is just like die, only happier. We can't just add a lexical item, laugh, and be done with it. We have to add 5 new lexical items. Okay? Anytime we try to add a new intransitive verb that behaves exactly the same as die to our language, we have to add 5 new lexical items. Okay? So this is a redundant analysis, or this is an analysis that doesn't capture generalizations. It misses generalizations. And the fact that it misses generalizations is beyond just, our intuitive feelings about aesthetics. It manifests itself in the fact that in order to extend our analysis, we have to add a whole bunch of new things. So as we extend our analysis, our lexicon grows. Okay, not in a simple way. It's not just a one-word extension, one word. It's not just adding one word gives us a whole bunch of new things. We have to add a whole bunch of words in order to intuitively extend our analysis with one word. Okay, that's sort of a concrete, measurable, observable problem with this analysis. That's a way of making concrete, of making measurable the intuition that our analysis is missing generalizations. Okay, so what do? Well, guys that were in the syntactic decomposition class, you know what to do. Let's look at the parts of these words. Okay, so let's start with the lexical items of category perf. So died and been, and if we had more things, also broken, right? Perfectives. Okay. Now, instead of just brute lexical items, so we've been thinking of these things as brute lexical items. Look here, right? Die, died, dying, died, dies. Those are just lexical items, but we see that there's structure in there. Is, was, be, been. Those are just lexical items, but we see that there's structure in there. The tensed forms, those are just lexical items, independent lexical items, but we see that there's structure in there. How do we get that structure to manifest itself? Well, we have a way of talking about structure, and that is with lexical items and grammatical operations. If we see structure, if we want to have structure, we need to turn it into lexical items and grammatical operations. Okay? So if we think that there's something in common, there's a shared structure that underlie perfectives, well, we need to introduce it. We need to make there be lexical items. Okay? So let's treat died, the perfective died, as really a combination of the verb die and a perfective lexical item. And the perfective been, so I have been talking for a long time, is a combination of the lexical item be with that same perfective marker. Okay? So this tree for been, what do I mean by combination? I mean it's a syntactically died, the perfective died, is not a lexical item. Rather, it's the result of, it's something that we construct in the course of a derivation. And what does it look like? Well, it looks like that thing on the tree to the right of the arrow. I'm using there a different notation for lexical items. Sorry, I'm going to come back to this over and over again in these slides. I couldn't decide, and I had made these pictures previously. So here I use a notation where all the features come first, and then the lexical item's name comes at the end, right? So here, so instead of having the lexical item name first and then a colon and then the features, we have features and then a dot and then the lexical item's name. Okay. So here, the head of that tree is the lexical item un, the perfective un, and its feature in this tree is just perf. Its sister has no more features, but its name is die. Okay, and likewise here with this bottom tree, I'm doing something sort of sneaky. That's not a, in order to treat that lexical item, the bin, as something that's been derived, we have to have combined be with a progressive thing, right? Because bin wants a progressive argument to become a perfective expression, okay? And so, but we can't, allow be to combine with a lexical item before it's taken what it wants, okay? So I have in a box, the sister of be in a box is prog. What does that mean? I intend that to mean there is anything in there of category prog, okay? Once we have that, then we can construct that structure which corresponds to, which will behave as that lexical item there, okay? So now we've decomposed died into a root verb die and an affix un. How do we end up pronouncing it as one word, right? We've gone farther away from the data. Well, we have a post-syntactic morphology. There are a lot of them, right? There's distributed morphology, mirror theory, head movement, all sorts of things, okay? They're actually much more common than you might think. I think they're virtually identical. They're instances of the same underlying abstract syntax morphology interface. But they presuppose that certain syntactic configurations can give rise to morphological composition. Okay? In particular, the head complement relation. Or you and the head of your complement can enter into some special morphological relationship with one another. That's head movement. Okay? So let's actually get this thing done. Okay? We can have morphological word formation during merge. Okay? So let's have a new kind of feature, a new kind of selection feature, one that says, oh, by the way, I want to enter into a special relationship with the head of my complement. Okay, I'm still going to write the equals, but now I'm also going to have a little arrow too, an arrowhead, and that's going to just mean, hey, I want to merge with this guy and I want to form a unit with his head. Okay, so if we have a pink affixal, a pink tree whose head is an affix with feature equals X, where he wants to form a morphological word with that thing, and it combines with something else whose head is W, that starts with the first feature X, then what we get is the same kind of thing we would have gotten originally, right? We check those features, but we also do a head movement step, okay? So what happens then? Well, we leave behind in the blue tree, we take the head away, they take the pronounced part of the head away, leaving the features behind. And so the only pronounced thing that's left is the empty string. And we take that pronounced head and we put it in the pronounced bit of the pink guy's head. Okay? We still need to specify how that, thing is pronounced because it's no longer a lexical item. So for that we need a theory of morphology, but here I'm just going to write a list. Okay? Morphology is just a way of compressing these lists, this list. Okay? So now what do? The entire reason for that foray was so that we could have a way of assigning features to our affixes. So this perfective died lexical item is now reanalyzed as a syntactic combination of two lexical items, okay, giving rise to that tree. We do our grammatical reasoning in the exact same way that we did it before, and we arrive at these lexical items. Die, which is of category X for some mysterious category X, and then of course I didn't write the lexical item in this format for writing lexical items. I wrote it with the the pronounced bit at the very end, right? So I'm mixing my ways of writing things here. But un's feature bundle is this head moving equals X and then perf. And that's what you have to give it in order to build the structure on the left. Moreover, because we've made a complex head, we have to say how that is morphologically interpreted, and we say that die plus un is morphologically interpreted as died. Okay? And we have to do that because the sentences that we build are not John will have died, but John will have died. Okay? So we do the same thing with the perfective bin, and there we see that B has to have features equals prog and X, and un has the same features as before. Okay, and B plus un is bin. Okay, we do the same thing. We just do the same thing. Has, had, is, and was. We break them into have and s, have and ud, be and s, and be and ud. Okay. Now, I say we have two versions of the present and past tense morphemes. Why is that? Well, because one version was built by decomposing has and had into have and tense, and the other version was built by decomposing is and was into be and tense. And there's no reason to give those things the same features, right? Because they're decomposings of different words, of different roots. Okay? So we have two copies of what intuitively should be the same morphemes. Okay? So we have three options. And we see that we have two copies. Copy is a little extreme because these aren't actually copies. Say the dash S guy, the present tense S, there are two versions of it. One where its first feature is the head moving selection feature for X, and the other one where its first feature is the head moving selection feature for Y. Other than that, the feature bundles are the same. Okay. We'd like there just to be one present tense marker and one past tense morpheme. So what can we do? Well, the way we can eliminate one of them while still allowing ourselves to derive so if we just get rid of one of them, then we're only going to be able to make has or had, but not is or was, or we're only going to be able to make is or was, but not has or had, right? So what we need to somehow keep both. We need to somehow have one version that is able to do what both of these previous versions did. So here's what we could do. We could say that X and Y, those feature names, are actually the same thing, right? So we erroneously kept them distinct here. Okay, that's one possibility. Another possibility is to say that they aren't the same, but every x is a y. Okay, so that means we can get rid of the present tense marker, present tense lexical item who wants an x, because every x actually is a y. And so we can just keep the one that wants a y, and it will be able to merge with x's because x's are y's. But wait, Greg, you might say, our features can't do that. Our features can only match or not match. We don't have a way of saying they don't match, but this is a special kind of that one. Right? We aren't able to do that yet. That's right. But we can still sort of do it. We can sort of get things to work out like that by adding a lexical item, which has no pronunciation, and all that it does is take an x, keep the head the same, move the head of that x up to this new head, and turn it into a y. Right? That lexical item reifies the idea that every x is a y, and it reifies that by allowing us to take an x and turn it, without changing its pronunciation, into a y. Okay? We sort of change its pronunciation, but only by moving its head. Okay? Or we could say that, well, x's and y's are related because every y is an x. Okay? So then we can get rid of those tense lexical items that specifically talk about y's and just keep the ones that talk about x's, because we can turn y's into x's, and then we can combine them with s. Okay? So those are three options that continue to allow us to derive has, had, and is, and was. Okay? And we only have one version of each tense morpheme. Okay? So which option of these is right? Right? They make different predictions. Here are some facts. Whenever you have and be, have always precedes be. And whenever be occurs incorporated into s or ud, have isn't present. And so these argue against the first option, treating have and be as having the same category, right? Because if they had the same category, there wouldn't be this asymmetry. Okay. There's still two more options. We'll talk about them in a bit. But we have the same difficulty. We have the same difficulty over and over again, right? We have the same difficulty with the perfective un, right? Because we can have, say, perfective be, been, and we can have perfective verbs, died or broken, right? Those have different categories. Be, been has a different distribution than died. So we have the same three options. We can either say that v and whatever this other category y is are the same. We can say that v is a y or the y is a v. Okay. Again, because been or be and die have different distributions, we don't want to say that their categories are the same. Right? So, moreover, if we assume that v is a y, so the second option here, and that y is an x, the third option here, then we allow v to also be an x by saying first, oh, it is a y and y is an x, therefore v is an x. Okay? Then we predict that die can also incorporate into s and ud, as actually is the case. John dies and John died. Okay? So that's what we're going to adopt. And if we have that reasoning, if we follow this reasoning throughout the lexicon, we arrive at these set of lexical entries. Those two lexical items that have this epsilon pronunciation, those are the lexical items that implement this is-a relationship. The first one says that every y is an x. The second one says that every v is a y. Okay? This is our lexicon. It doesn't look much smaller than the one before, except it's not much smaller than the one before, a little, but not much. Except it has one great advantage, which is that in order to add a new verb, we just add a single lexical item. Right? Laugh in all of its forms can be added to this lexicon by adding the single lexical item laugh of category V. Okay? So this means that the redundancy, the featural redundancies, the missed generalizations that we saw are no longer missed. Okay? This structure here is sort of a schematic representation of the way things work. So verbs are merged with ing to make a progressive phrase, which is merged with be. Be is merged with un to make a perfective phrase, which is merged with have. Have is merged with will or a tense lexical item to form an S. Right? And those arrows underneath these things are head movement arrows. Okay, this was our analysis. That's what we ended up with. Okay, and the reasoning we did is what I think of as a decompositional kind of reasoning. And that said, whenever you have a lexical item, UV, which is just, UV is its pronunciation, we're going to just chop it in half somewhere, with features, with feature bundle beginning with alpha and then ending with beta, you can split it up into two lexical items. One is U, with features alpha and then some category X, and the other one is a suffixal, a head moving V, which wants to select an X and do head movement, and then continue on with the feature bundle beta. Okay. So with this decompositional methodology, what you end up with is a whole bunch, from one lexical item, you end up breaking it up into potentially a whole bunch of new lexical items. One of them is the root. This U guy is the root, he's the lowest one. And these other lexical items are suffixes or affixes, which want to attach to this guy, and they're higher ones. And these are often called functional projections. So this methodology is just going to engender the proliferation of functional projections. Okay. So the reason why I think in transformational grammar you have a bunch of functional projections is because everyone is really doing this decompositional methodology. And it leads to functional projections. Okay, so we have some time. Let's also talk about raising to subject, because now we can talk about movement. Okay, this previous thing was introducing merge, feature bundles to control merge, and head movement. Okay, head movement is not a special kind of movement. It's just essentially a phonological effect that happens during some mergers. That it happens is determined by the kind of feature you have. Right? Here we have say an equals V feature. That is a head moving feature. It's a head moving equals V feature. Okay, so head movement is a reflex of some merge steps, and it's a reflex of those merge steps which are triggered by head moving merge features. Okay, so let's expand on our analysis. So verbs like seem allow for the following alternation. So what I mean is I want to generate these new sentences, right? Our previous grammar, our previous analysis was able to generate some English sentences, but there are a lot more English sentences, and I'd like to generate them all, okay? But I'm not going to generate them all at once. I'm going to expand our analysis slowly, okay? The next batch of sentences I would like to account for are those in 1 and 2. It will seem that John laughed, and John will seem to have laughed, okay? So how do we do this? Well, there are some lexical items there that we don't have, right? We have John and laughed, and we have laughed, but we don't, and we have will, we have John, but we don't have it, we don't have seem, we don't have that, and we don't have to. So let's add them, okay? So we need to have 2 seams, because each seam here selects a different kind of argument, right? We don't want to have John will seem that John laughed, and we don't want to have it will seem to have laughed. Okay, so the 2 complements of seem need to be of different categories, so we don't overgenerate, and so there have to be 2 seams. Okay. The way I got to these new lexical items is I drew the tree for it will seem that John laughed in just the same way. So we have subjects and predicates, and the predicates are sort of right branching, right? So that was the head of that John laughed. To is the head of to have laughed. And then using the same sort of grammatical reasoning that we had before, we worked backward from those structures to lexical items. And this is the result. Okay? So some observations here are that it as a main clause subject requires a finite that complement, and a DP as a main clause subject forbids a finite that complement. Right? That's we see that that's what's going on. But we don't have a way of transmitting this information from one point to another, so we had to encode it in the categories. Right? There have to be two seams, one that says, oh yeah, I'm taking a non-finite complement, that's the equals I seam, and another seam, one that says, I'm going to take a finite complement, that's the equals C seam. Okay, they have to be different. Okay, but in order to just have one seam, we would have to be able to transmit information about the subject to the seam, or vice versa. We'd have to transmit information about the kind of argument that seam took up to the subject so it could pick the right kind of subject. Okay? That's the fundamental problem that we have. And that's what's stopping us right now from just having one seam. But we'd like to have one seam, right? Again, we see, oh man, we're missing a generalization. There's got to be some better way of doing this. So here are some possibilities. We could have syntactic feature percolation, okay, which I'm sorry, let me back up a bit. These lexical items don't work, right? They overgenerate, right? Because it is a D, and we want it to be a D because it combines with will. We could also have, for one, John will seem that John laughed. And for two, we could change John with it because they have the same category and get it will seem to have laughed. And we don't want those. So our lexical items that we actually have give us the wrong overgenerate. Okay? And we need to rein them in. We need to restrict them somehow. This is not about unifying seam and seam. We'll do that in a little bit. Okay. So how do we restrict them? Well, the problem is both seams, after they take their argument, their complement, either the IP or the CP, they both give us back V's, right? So the distinction between the kind of complement they took is gone already. It's gone. And so we lose this information that we need to have in order to decide whether we want to merge it or John. Right? We've lost the information. So what could we do? Well, one thing is to keep the information, right? And say that, oh, well, the two different kinds of seam, they take two different kinds of complement, and we have to remember which kind of complement we took. So there's a seam, the seam that takes the CP, it doesn't give you a V, it gives you a slightly different V, okay? And this, it gives you a V with the information, oh yeah, I'm there because seam took a finite complement. And that information has to be doubled on all of our auxiliaries. Will needs to take not any old x, but only an x that merged with something, that merged with something, that merged with a v that had taken a finite complement. Okay? And then that will doesn't take any old dp, it only takes a special dp. And that kind of special dp is the kind of dp that it is. Okay? So we've doubled our features, we've doubled our lexicon, so that we can encode on the features what kind of complement seam took. Okay? And we can do this without changing the mechanisms of our grammar. Right? This is a conservative solution. Here's another possibility. You can say, oh, no. It's all semantics. Right? So if you take a finite clause, a finite complement is just a proposition, whereas a non-finite complement is a function from an individual to a proposition. It's a property. Okay? So seem, that takes a finite complement, it wants a proposition and it will give you a proposition back. And there's a will that wants a proposition to give you a proposition back. And it, well, it doesn't mean anything. It takes a proposition and gives you the same proposition back. Okay? So if we use the equals CV version of seem, that's going to have one kind of semantic type. And if we use the seem that takes a non-finite complement, then there's a version of will that wants a property of propositions to give you the property propositions back. And John is going to be an individual, and so we can combine that with that kind of will and get a proposition. Okay, we can do this in the semantic type. Okay, what's going on here? Well, we are encoding on the semantic type information about what kind of argument seem took. Or maybe a better way of thinking about it is, maybe that's not such a good way of thinking about it. These different kinds of seams have to be different semantically, right? And so in order for things to combine with them, well, they should probably be different semantically too. So we have to have 2 copies of will and 2 copies of have and 2 copies of be, etc., etc. And since we have to have that anyways in order to get things to combine, let's just use this information. Okay. It's already also built into what we have anyways. Okay, but there's a third possibility, which is the one we're going to pursue, and that's the ninja technique of Kagebunshin no Jutsu. And that's the shadow clone technique. And that is that the main clause subject is in 2 places at once, right? And you have to satisfy properties of both positions to be well formed. Okay? Whoa. I mean, I say whoa, even though you guys know what I'm talking about. So what does John will laugh mean? Well, it basically means that it will be the case that John laughs, right? So its surface structure looks like this. Will, so John is an argument of will on the surface, but as on the semantics, we see that he's an argument of laugh. So the surface structure could be generated by putting the equals D or the D equals feature on will, but the semantic structure, so to speak, should be generated by putting the DP selection feature on laughs. Okay. This is just to motivate the plausibility of the ninja technique. Okay. We want the D to be in both places at once, but it's not quite right to do this by actually having both of those things have a D feature, have an equals D feature, because, you know, there's only one D, and this would make us want 2 of them. Okay, so a DP should have 2 positions, one where it's base generated and one where it appears on the surface. Okay. In order for that to happen, it has to be syntactically activated after being merged, right? It has to be. But merge deletes the D feature, right? But then it has to have another one. Okay. We don't have a way of checking features after something is merged, right? So we need a new operation. And so, here's one way of representing it. So here blue is a maximal projection, this blue guy is a maximal projection. And we see that we have this, on the left-hand side of the arrow, we have a structure that has a maximal projection in blue. And then on the right-hand side of the arrow, we have a new root that also is connected to that blue guy. And so blue here is literally in 2 places at once. That's what we want. Okay. Here's a version of move that's more familiar. It's with traces. A trace isn't necessarily a magical thing, but it doesn't matter because we can get rid of it anyways. It stands for a leaf that has no pronunciation and no features. It's as a silent leaf with no features. So what do we have? We have our structure on the left, which is a big tree that contains a blue maximal projection, and moving that blue maximal projection just takes that guy and moves him to be a specifier of the red guy. Okay? The red guy is still the head of everything. Okay, that's what we want. Now here, the blue guy is not in two places at once, but he was in both places at some time or other. Okay? Again, just like with merge, we don't just want to do this willy-nilly because that's not how language actually works. So we need to control when we can move things. How did we do it last time? We used features. How do we do it this time? We use features. It's the tried and true solution. So let's have different kinds of features this time, right? Because the equals features are for merge. Let's have plus and minus features be for move. So plus y says move something to me, and minus y says move me somewhere. Okay, we're going to have two kinds of features corresponding to the two roles that the mover and the movee play. Okay, so the guy that is saying, hey, move to me, has a plus y feature, has to have a plus y feature as the first feature of its head. And the maximal projection that's doing the moving has to have a minus y feature as the first feature of its head. Okay? And then in the resulting structure, you get rid of the plus y and the minus y because their desires have been met. The guy that wanted to move has been moved, and the guy that wanted to have someone moved to him has had someone moved to him, right? So everyone is happy. Get rid of the features. Okay, so this is what we wanted. Now we can fill it out a bit. So a DP should have two positions, one where it's base generated, which happens via merger, and one where it appears on the surface, which now happens via movement. Now we have an operation that lets us do this. It has to be syntactically active after it's been merged, and merge deletes its D feature, so it has to have another feature. Let's call it minus K. It has to be a minus feature of some sort because it's moving. It has to have some name. Let's call it minus K. Okay, so a DP feature bundle is going to be of the form D and minus K. D tells us how to be well formed in its base position. It could be in a base position if that base position wants a D. And minus K tells us how to be well formed in its surface position. It can be in a surface position if that surface position wants something of category K there. Okay. So this is what we had wanted, but it was not really right. And so this is the ninja technique that we were after, right? So we have laugh that has a D equals feature, and will doesn't have a D feature, it has a plus K feature. So will says, hey, someone that wants to move, come to me. And laugh says, hey, I really want a DP. Right? So the fact that laugh has a D feature allows us to have John, so to speak, affiliated with laugh semantically. And the fact that will has a plus K feature allows us to have John not next to laugh phonologically. Yay. And that, boys and girls, is the story of why there is movement. Okay, so that's going to be our solution here. And the reason that we want this is so that we can enforce the dependency between it and a finite complement and John and a non-finite complement. Right? We couldn't do that with just the lexical items that we had extracted via our grammatical reasoning. We could have done it by duplicating our lexical items so as to encode on the features, hey, what kind of complement did seem select this time, right? But we decided to do it differently without having to double up on our lexical items just to pass information around. And we did it by adding new operation, movement, okay? So now we have to update our lexicon. So we saw that we want to have on the will feature, not an equals D feature, but a plus K feature. And we saw that we want to have in our intransitive verbs, not just a V, but an equals D V. Now we want intransitive verbs to select DPs. And now we've seen that our DPs need to have not just a D feature, but also a minus K feature. So now we have to update our lexicon accordingly. Okay. So what used to have a D equals feature that now should be a plus k feature? Well, the d equals feature on will in the past and the present morphemes. Okay, they were originally intended to introduce the argument in its surface position. But now we've decided that the arguments don't get merged in their surface position, they move to their surface positions. Okay, so we have to assign our tensor lexical items the following type, equals x plus ks. Okay, and by tensor lexical items I also mean will, right? Sort of a future tense. Okay, some of them, like the suffixes s and ud, that first equals x is going to be a head moving equals x. Okay. Now, crucially, the infinitival to doesn't provide a surface position, and so it doesn't have a plus k feature, even though it selects an x. Okay. So here's how we derive raising to subject. So we can build, in the process of building the sentence John will laugh, first we merge John and laugh, and then we merge will. And we have this structure here. I've done a couple of head movements. Okay. In this structure, John is a maximal projection, right? The leaf John is a maximal projection of it by itself, and it still has a feature. It has a minus k feature. Okay. The head of the entire tree is will, and it has features plus k and s. Okay. So this is a perfect situation for movement to apply. And there we go. Movement applies, canceling out the plus and the minus k features. We end up with this structure, and it only has one unchecked feature. It's at the head, and it is a simple category feature. So this is a sentence, and it's pronounced John will laugh. Okay. We can do the same thing with seem. Right? So here, seems, right? So the plus k here comes from the s, the present tense. Seem has been head moved up to it. So we built this structure, seem with present tense, with no have or be. The laugh John merged with to, and then that's the seem merged with to as well. John has a minus k feature. That seem guy has a plus k feature. Oh, that's wonderful. A match made in heaven. John moves up there, and we have a structure, a complete structure. It only has one feature, and that is a category feature at the head of the root. And it's pronounced John seems to laugh. Yay. Okay. We can add as many seams as we want. Okay, and only after we add a tense item do we actually trigger raising of the embedded DP. Right? So here's one seam, here's three seams. Let me see here. This represents the structure that we build when we take an X expression, add a to, merge that with seam, skip over or turn our V into a Y and turn our Y into an X with these empty category changing is a lexical items. Okay, so the important thing here is that by doing these steps, we take an X and build onto it, and we get an X. And so we could do this over and over and over and over again, right? And so here we did it through 2 times. Okay, seem to laugh into John. Okay, so that's great, wonderful, yoo-hoo. But how do we deal with this alternation? Right, that's our ultimate goal. Now we can derive John seems to have laughed, and it seems that John laughed. Well, we can't really do it yet, but John seems to have laughed. We get that. Well, we see that it appears as the subject of tensed clauses without semantic subjects. It seems, it rains, yada, yada, yada. That's what we sort of intuit. But from the perspective of our analysis, it appears whenever we have a plus k feature with nothing to check it. Right? This is the last resort of it. It appears when And we need a subject. We don't have a subject. Okay. So, right, it has to have a feature bundle ending in minus k, because it lands in a plus k position. It can only do that if it has a minus k feature. Okay. But it can't be a D because it doesn't behave the same as a regular DP, right? It has a different distribution. It is different from a DP, so it can't have D minus K, because then it should appear everywhere a DP does, right? But it has to end in minus K. So, but it has to have some other category feature to be selected in the first place so we can get into the structure so we can move it all. So let's give it a new category, one that hasn't been used before. Let's call it an expl, which is short for expletive. Okay. All right. So now we have it, but nothing selects an expletive. Well, let's for the sake, just for fun, treat it as a VP adjunct. Okay. What does that mean? Well, it means that we want it to be freely merged at the VP level, but we don't have a way of doing that. In order to be merged, something has to select you. Well, how can we simulate free merge with lexical items? We can have a silent lexical item that takes a VP, selects an expletive, and then turns into a VP, right? So it's as though it looks as though you just stuck in an expletive, even though the thing didn't originally want it, which is a junction. But really what happened is you just did your totally normal merge steps. You just had a silent lexical item you couldn't see. Okay? All right, and so now we can add an it on top of, say, our seam. Right, so here we've taken seam, selected a CP, added an it, and then everyone is happy. Okay, so now we have a way of deriving the sentence, it seems that John laughed. Yeah, awesome. But it's never so easy. Now we can generate as well, John is believed that it seems to laugh. How does that work? Well, first John is merged with laugh, seems to laugh, but then we adjoin an it, add a present tense, it checks the K feature of the present tense, add a that, well, we don't have is believed, but let's imagine. And now we want to move something. We've already moved it. Oh, let's just take John. He was still there all along. Okay. So the problem is intuitively that nothing enforces the last resort character of it, right? Really, we shouldn't have adjoined it in there because we already had John. Why bother adjoining it when there's John already? Right? You should only adjoin it if you have to. Okay. So how can we cache this out? Well, before we move it in the John is believed that it seems to laugh sentence, so right at seems to laugh, before we move it, this is the thing that we have. And if you zoom in, you see that in red, helpfully, there are two expressions who have the same first feature minus k. So those guys are competing to see who is actually going to be able to move to the plus k position of seams. Okay. Aha. This seems like a configuration that, this is a configuration that if we could stop it from happening, we could block this derivation of an ungrammatical sentence. Right? So what could we do? Right? What kind of stipulation could we make so that it isn't the thing that we move here? Well, one thing that we could do is we could always move the lower candidate. Right here, John is lower than it, so maybe we should move John instead. Like if we ever have a situation where there are two things that have the same first feature, we should always choose to move the lower one of them. Right? That's possible. Another option is to say, you should never have to make a choice like this. Yeah, whenever you have a choice, that's bad. And another option is, yeah, we should treat it differently. This is the wrong analysis of it. So even though if this is, we don't even need to think about this. Okay. I think that the second option is the one we should pursue. Okay. And the second option is give up and run away. So why should we do that? Well, let's think about it a little bit. Whoever you don't choose, right? If you choose the top guy, then the bottom guy, whenever he gets to move, is going to have to move longer, a farther distance than he would have had you chosen him. If you choose the bottom guy, then the top guy, whenever he finally gets to move, is going to have to move a longer distance than he would have had you chosen him here. Right? So whoever you don't choose, that person is going to have to move longer, a farther distance than he otherwise would have. Right? So this is sort of a shortest move flavor. Okay. So that's sort of motivating this from sort of an intuitive perspective. Well, giving up is also easy because you don't have to compare things. You don't have to calculate. You don't have to see who's farther away. You just say, oh yeah, I bail. Right? It works pretty well. And my favorite reason is that it's formally, from a computational perspective, it's awesome. Okay. So this giving up strategy is going to be called the SMC, and it's going to be implemented in the following way. Move as an operation, is only defined. So if you have a structure where the head of the root starts with a plus feature, and there's a maximal projection inside that has the matching minus feature, so if move could be performed, it has to meet another condition in order to actually be performed. There can only be one thing, one maximal projection with a matching first feature. Okay? So there can only be one thing in there with a minus feature that matches the plus feature on the root. Okay? If there's more than one, then you're not allowed to use the move operation. You're just dead in the water. Okay? So what are some constraints on movement? Well, there's an attract closest constraint, which is the opposite of the move the farthest, right? Should always move the lower candidate. I didn't choose that because that's the exact opposite of what current dogma says you should do, right? But that's one of the things that people say. You should always move the closest guy. It doesn't work in this case. Another kind of constraint on movement is what you might call a specifier island constraint, which says you can't extract, you can't move out from inside of a specifier. And another constraint is this one here, right? The SMC. Or more generally, you can only have at most k guys competing for the same position at any time. Okay? But the SMC, as I stated it, is you can only have one guy competing, which means there's no competition at all. Okay. And I said that the SMC was formally awesome. What did I mean by that? Well, we can actually look at the kinds of patterns you can derive with various constraints on movement. Okay. So we know that if we have the specifier island condition that's active on specifiers created by movement, then you can do everything. You can write a lexicon that will that can do exactly what Windows does, right? On the operating system Windows. You can write Windows using a lexicon. Okay. You can do anything. There's nothing that you can't do. Every single pattern that can be described can be given a lexical and grammatical analysis. Okay. If you don't have anything, if you don't just say, yeah, do whatever you want, or if you have attract closest, then it's not clear exactly what you can do, but you can do a whole bunch. Okay. The membership problem is at least 2x space hard, and maybe it's undecidable. It's equivalent to the provability problem in a certain kind of logic. Okay. So there are things you can derive, there are patterns you can describe if you make these assumptions that we don't see in language. But with the SMC, then you can only describe a certain class of patterns that looks very language-like. And with the SMC together with the specifier island condition on specifiers that are created with merger only, then you have a restriction on this already restricted class of things. Okay? So the constraints you adopt on movement really, really matter. They really matter. Okay. They matter for the kinds of things you could possibly describe. Okay, so, but we're not going to get into that too much because it doesn't really matter. So this is already too long, but I want to finish this section. We're almost done. The SMC at work. This expression here is generated by our analysis. It has two maximal projections whose first feature is minus k, namely this leaf it and the leaf John. We can still do stuff to it, but we can already look at this and say, yeah, we can never get rid of those minus k features. Never. Is if we add a plus k feature somewhere, the SMC is going to say you can't move anything to check it because there are two guys, at least two guys in there. So this expression here, even though you could still do stuff to it, it's dead in the water. It can never, ever become a complete expression. Okay? This expression is also generated by our analysis. Right? It also has two subtrees that have a minus k feature. It can also never become a complete expression. Okay? Even crazier things are in the language we generate. Okay? But they're all blocked by this constraint on movement from ever becoming complete expressions. What that means is, even though we have nothing stops us from adjoining an expletive it whenever we want. If we do it willy-nilly, those things that we build are just sort of, it doesn't matter. They're already broken. They're dead in the water. So even though we can build a whole bunch of garbage, that garbage is filtered out before it becomes a complete sentence and thus would overgenerate. So we overgenerate our language, but that doesn't matter because we only care about the complete expressions of our language. And the things that we overgenerate aren't complete, and so they don't matter. Okay? So, how do we derive our it sentence? Well, we have seem that John will laugh. We adjoin an it. We head move our seem up a bit. We add a present tense, and then we move our it. Okay. So it as a main clause requires a finite that complement. A DP as a main clause forbids a finite that complement with seem. That was what we observed. The problem was essentially how to transmit information about the complement to the subject choice. And the solution was the main clause subject is in two places at once, and it has to satisfy properties of both positions to be well formed. Okay, but we still have two lexical entries for seem. Right? That's not what we want. One wants a CP and one wants an IP. Okay, one wants a finite clause and one wants a non-finite clause. But so far in our grammar, there's no point to this distinction between I and C. There's really no point in making this distinction because nothing depends on it anymore. Right? The alternation, the dependency, the informational dependency between between the kind of complement clause and the kind of subject is now cashed out by the SMC. Right? We need to have something with a minus k feature in order to check the plus k feature of a finite tense guy. A normal subject a normal DP has it, and he's alive in a non-finite clause. Okay, but he's not around in a finite clause. And so for the finite clause case, you have to add an it so you can check this plus k feature. Okay, so the distinction between I and C doesn't matter. We can just get rid of it. We can call everything C. Okay, and that makes the distinction between seem and seem disappear. Okay, Rain and snow, no problem. Rain and snow differ from laugh and die in not selecting for a DP at all, right? And so in order to have a sentence, a finite sentence that's going to want something to check its plus k feature, we have to adjoin an it. Okay? So that's, I went slightly over. I wanted to talk about this stuff. Hopefully the mechanisms of the grammar are fairly clear. We have merge and move. They're controlled by features. We have a constraint on movement, the SMC, which simply says you can't do movement unless there's only one guy that wants to move to that position. And if there are two things that want to move to that position, then you just give up. The derivation crashes, if you will. Okay? That's where we want to begin next time. Thank you very much.